It is my honor to present you today a little bit of my work. And the work is about the application of network calculus for reliable and predictable behavior of IEEE 802.1 CB, frame replication and elimination. As you already know, my name is Lisa Maile and Erlangen-Nuremberg is in Germany. So what will this talk be about? I want to show you that all of the things that we derive here can not only be used in the typical use cases, which are getting worst case delays, getting worst case buffer sizes, but we have also another application area, which might not be known to you yet, which is the safe configuration for duplicate elimination. I think this is the old slides, but it's okay, I can work with it. The TSN was done to ensure reliable, ultra low latency traffic. And if retransmission is not an option, then it duplicates the same packet over multiple disjoint paths. And this is defined in the standard, which is IEEE 802.1 CB. The whole name is frame replication and elimination for reliability, but I will only say FRARE. So, and what FRARE does is it sends packet over multiple paths, and of course, at a so-called elimination device, it forwards new packets. We want, of course, to receive them, and it eliminates duplicate packets. The elimination of duplicate packets is important because the application should not be aware of the underlying network operation. The configuration of this identification of duplicate packets is defined in the so-called sequence recovery function. And there we have several parameters with which we have to set. However, currently in the standard, it is written that it is up to the user to match the needs of the particular network. But if we are in the context of ultra reliable traffic, maybe it is not the best idea to leave the configuration completely up to the user. So, and there is where we come in place now. First, to give you a short idea of how this is structured, in FRARE, we configure every flow that needs this reliability separately. And the flows have special characteristics, which are listed here. So in general, it has every stream sends at most MIF packets during an interval of length CMI. And in every interval, it can the packets are smaller or equal to MFS. So for periodic traffic, we can see here, sequence number 101 would be sent at this timestamp, and after the sending interval length, the next sequence numbers would occur. And now everything else that we need to be on the safe side is the lowest delay of the fastest path and the highest delay of the slowest path. And we know how to get there, right? So here's the application of network calculus. So with these two information, we now know that sequence number 101 can never arrive earlier than this time. That's the best case for the slowest path. And it also can never arrive later than after its worst case delay. It's either lost or it will arrive before this time. So the difference between these two times we call reception window. Only during this time we can receive packets of this sequence number. So with this information, we can now tackle 4 main limitations of the current standard, which is we have to find the correct algorithm to identify duplicate packets. We also need to take care of how much memory do we need to save this information, and some timer values and some side effects. Yeah, we have published this in IEEE ICC, in the IEEE conference ICC this year. And for simplicity, I will only tell you how to do it for periodic traffic with 1 packet per interval. If you're interested in jitter, aperiodicity, or multiple frames per interval, then I will refer you to the paper. Yeah, to shortly give you an overview again, so we are in the middle of this network here. So we only need the delays from the duplicating device to the eliminating device, not the whole end-to-end delay. And what is happening after the elimination, that is investigated in detail by Ludovic, as you have already heard yesterday. So my area will be here, and I will now discuss what can we do with this worst case delay in the network. So first, to identify duplicate packets, FAIR offers two different algorithms. Let us start with the simple one. This is called match recovery algorithm. And here, only the highest sequence number that we have received is stored. And we identify all duplicates with this sequence number. All other duplicates are simply forwarded. Well, this is very simple, and the standard says that this will only work if we have a special stream characteristic. They call it intermittent. This means that the difference between sequence numbers may never exceed 1. But how do we know whether we have an intermittent stream? This is what we have now defined. So to identify intermittent streams, or to ensure that they are intermittent, we have to ensure that all copies of one sequence number have arrived before a new sequence number can arrive. And if we look at this graphic here, you would see that for 101, a copy of this sequence number could arrive after 102. So in this case, the stream would not be intermittent because we could not identify, we can only store one sequence number. So the solution is that the reception window for a safe configuration needs to be smaller than one sending interval. So with this simple configuration, we know that the streams are intermittent. We can use the MRI. We have proved our configurations both theoretically and with simulation, which we set up in Omnet++, you might all know, using the library nesting. And in this simulation, if we vary the different path delays and look at the resulting configuration, then we see with our configuration, no duplicates are passed, whereas with lower configuration values, we have duplicates, and also we have exactly met the border here, so it shows that our results are not too cautious. To put this into the context of network calculus, so I thought it's interesting if we compare it to like the existing rule of thumb. Unfortunately, there's not the formula here. I've edited yesterday evening, but the slides, yeah, it was too late, obviously. But in the standard, there's the IEEE 802BA standard. There's a formula which is a rule of thumb, basically just some net hardware delay, some preemption delay, and then we just assume that for a certain amount of time, there arrives the whole reserved bandwidth. And with this existing worst case delay calculation, which is just a rule of thumb, actually the match recovery algorithm could never be used. Why not? Because the standard also forces us for the highest priority for the CBS scheduler, which is my main topic, that the sending interval is always 125 microseconds. While their worst case delay calculation, even for small path differences, will always result in a bigger delta D. So they can never use it. Luckily, they have us, so we can use network calculus, and at least for small path differences in this very simple network, we can use the MRI algorithm. But even so, we have a very simple network here with no cross traffic coming here. So we have the serialization effect, we have link shaping. The network calculus boundaries are very easily calculated here and very low. So what we have to know is that even with network calculus, the MRI algorithm is not that applicable. Well, so to take away with. And if we cannot apply the MRI algorithm, then there's another algorithm that is proposed by the standard, which is called vector recovery algorithm. And instead of storing only one sequence number, we now have a sequence interval with the length of the sequence history. So here we assume that sequence number n is arrived, and we have a history which tracks whether the sequence numbers have arrived or not. And we also cover the same length in the future. So what happens now if a new packet would arrive? If it is within this interval, the sequence number, so for example, just the next sequence number would arrive, it would be the next packet, everything would be good, it would be passed, all good. If we have it in a lower sequence number, we can safely identify whether it's duplicate or not. If it is higher, we simply shift the interval to this new sequence number. But what happens if something arrives outside of this interval? In this case, all packets outside of the interval are simply discarded. And currently, the only guidance that we have is a default value, which is written in the standard, which is simply set to 2. Well, but we have, of course, to ensure that no packet arrives which is not in this history. So we can, for example, only drop out packets of the history if they can no longer arrive. And for this, we now have to keep track of the overlapping reception windows, which we have illustrated with this function and denote it as n. So at this time, we have 3 overlapping reception windows. Currently, a sequence of 101 would arrive, and indeed the next sequence number that could arrive could be n higher, so in this case 3 higher, 104, because they could be delayed. So we have to store at least n higher and n lower. It's the same argumentation for the history as well. But since the history is only updated at the reception of a new window, we have to get rid of this ceiling function. So this is the resulting safe configuration. And again, our simulations show that packets which are outside of the interval, they are called rogue, never occur with our configuration. For the network calculus results compared with the rule of thumb, this means that we can save some memory. So for this simple network, we even can halve the memory that we need for the safe identification. So one more problem that we have not thought about is what happens if a packet is lost before it is duplicated? Well, then an arbitrary number of packets could be lost. So of course, the next interval which arrives can be outside of the interval of the history length. And for this reason, FREYR has introduced a timer. And this timer resets the sequence history. But if it is too short, then before a duplicate would have arrived, we have reset the history. And therefore, we have reset the history, therefore duplicates would have been passed. If it is too long, new packets would be discarded. So we have 2 steps to identify the safe configuration. When we put it bigger than the reception window, then we know that this packet has been lost entirely, so we can definitely reset the interval. But if the reception window is small and the length is long, then we could, of the sending interval is long, then we could reset between every sending interval, which is unnecessary. And here we have showed that for the safe configuration, we safely identify duplicates and pass all packets, but we have an unnecessary number of resets. For our optimal configuration, everything works, but if we get too high, we don't pass valid packets. So indeed, our configuration, which we came up here, is safe. This one here, I just have left because I just shortly want to show you some small thing. This topic here is covered by Ludovic Thomas. The only thing that I want to add here is, the topic here is if a fast link fails, then bursts can occur. And this has studied, as I said, by Ludovic. One thing is that we can derive the size of the burst and the length of the burst with this reception window with a simple formula. So to dimension the buffer sizes at the end. That's all I want to say here. And to sum it up, if we compare a more realistic network and derive the network calculus delays for different path lengths for path A and path B, with network calculus, everything works smoothly. With the default value, of course, we cannot guarantee any safe transmission. This is also changed because I got luckily accepted at the Communication Society journal. So we want to put this configuration of FREYR in our central admission control scheme, which we have done for the credit-based shaper. It's an online configuration, so we can say configure deadline-aware streams without reconfiguring already existing streams. We do routing, prioritization, and so on. And yes, in the future, we want also to add the automatic configuration of FAU streams. So thank you very much for listening. As I said, we want to add the reliability that the standard actually seeks to add. And luckily, we can do this by knowing the worst case delays. And we hope that we can help with this in future standardization processes. Thank you for your attention, and I'm open for questions.
One question on your interpretation of the source traffic standard. Can you show at the beginning where you showed the CMI?
Yeah. So here.
Yes, this one. Isn't it only one of two possible interpretations of the standard, assuming we apply the class measurement interval as any possible sliding window?
Yes, exactly.
As opposed to repeating windows that would lead to perhaps difference. So
the question was whether this interpretation of the stream characteristic is only one interpretation, because you could say, okay, the interval is periodic, but it might also be interpreted as a sliding window. And what happens then? That's the question, right? Yes. So exactly, that is that we also considered this, and basically it is similar then to a aperiodic or a jitter traffic. So we have added this also in our paper, and we basically just adapt the ranges a little. Further questions? Once again, can you please? Yes, it isn't the standard when you look at the young models. Oh yeah, sorry. Yes, sorry. So the question is, where is the default value of the history length of 2 coming from? And this is just, if you look at the standard, they're like the young models where they said, okay, the sequence history is true in the standard. So they have not talked about it. It's just given. And that's the only information that the standard provides about the length.
So maybe the question, you said that the match recovery algorithm of the range application is very limited. And I guess the main application for this was like what they call, the periodic point deadline flows when you send when you send a packet, you already know that the
yeah.
one has arrived. And I was wondering, like, if by your work that you said the application is limited, then is it limited to this only specific configuration of knowing when that my packet has arrived, my good packet has arrived, and I send the next one, or is it like a small stack in which you can envision other streams that could use MRI?
Yeah. So okay, the question was whether for the application for MRI, when can we use it? So is it really that limited, as I said? And here I have to say that the strong limitation of this algorithm, I only said here. It's not in the paper, because that's like a strong thing. It is. So there are 2 answers to this. First, the standard says that we need such a small interval of 125 microseconds. That's a really, really small sending interval. Like several applications have like one microsecond, for example. And then the area of application would improve because the sending interval would also improve. This is currently not possible, for example, in the decentral approach of TSN, but in a central approach, so in our case, we can define the interval as we want. So there, MRI could definitely be used more often. And also, so is it only used in cases? The question was, is it only used in cases where the deadline is below the sending interval? And the answer here is, if we have some information about the best case delay, we can add this as well. So it's a little slack here, but apart from this, this is the main area that we can use it. Yes, I think that's the answer.
So, is there a last question? So, thank you again.
Thank you too.